Okay, so in review question 22, we've got a 0.6 nanocoulomb charge. Sorry, I should have the word charge in there. It is fixed at the origin. Point P is located on the x-axis at x equals 0.3 meters. The second charge is placed on the y-axis at y equals 0.5. What is the sign and magnitude of the second charge? It's a net electric field at point P points in the positive y direction. Okay, so let's try to draw this somewhat accurately. Okay. Give myself enough room to calculate everything else. So I'll try to draw this so we use a sort of scale on my ruler here is 0.5 is 5 centimeters. And then we've got 0.3. Okay, so this is where our point P is located. We've got a 0.60 nanocoulomb charge up here. Sorry, at the origin. Then we've got some other charge here of y equals 0.5, and we know the net electric field at point P points in the positive y direction. So we have enough information to solve the electric field at point P due to the 0.6 nanocoulomb charge. Let's do that. So E at P at the 0.6 nanocoulomb will be K times 6 nanocoulombs divided by 0.3 meters O2 squared. Don't forget to convert your n to 10 to the minus 9. K is 9 by 9 to the 10 to the 9. So if I take this out, we should get 60 newtons per coulomb at point P. So I'll just draw a vector here to indicate that the field here due to the 0.6 nanocoulomb charge is 60 newtons per coulomb. But we know that the net field points in the positive y direction at point P. So how could that be possible? So we have some sort of net field. Let us draw lightly on my ruler here, around my pencil. So to get the net electric field at point P to point upward, this particular charge up here, the sort of second charge, has to have a component that points in the negative x direction of exactly the same magnitude as the 60 to cancel it out, and then it has to have some y component remaining. So the electric field at point P must point toward the negative charge, and it must have an x component equal to 60. So I'll just draw that in here as a dotted line of the same length, and I draw a line connecting these two. Second charge to point P, and see that its y component would be this big. So and that means that that's what the net field would be. So I'll draw that in purple. How tall is that? So this would be so E net. Okay. So let's try to figure out how do we find the size of the charge such that it produces an electric field at point P that has a 60 newton per coulomb x component. And I'm not sure where this y component is yet. That's the purpose of this question. And figure out how big that charge needs to be. Okay, so we know that the E at P due to the, let's say, charge 2, its x component is equal to 60 newtons per coulomb in the negative x direction. So what I really want to do is find out what is the magnitude of this hypotenuse, because that's going to be linked to the size of the charge. So what I need to do is figure out what this angle is, because if I figure out the angle in here, I can then figure out what the length of that hypotenuse is, and that will lead us to the correct answer. So what is the angle here? Theta. So we know that the theta, this small triangle here of the vector components, actually that shouldn't be a dotted line, that should be a solid line. It's the same as a similar triangle to the larger one, which has correct dimensions of 0.3x, 0.5 in the y. So theta will be equal to the tan inverse of opposite over adjacent, so it's 0.5 over 0.3 meters, and that should give you an angle of 59 degrees. So the E at P due to the charge 2 will be basically equal to 60 newtons per coulomb divided by the cosine of that angle. So 60 newtons per coulomb divided by the cosine of 59 degrees. You're sort of thinking a little bit about that. The cosine of theta will be equal to Ex over E. So E will be equal to Ex divided by cosine of theta. So that's what I have here. So this is equal to 117 newtons per coulomb. Okay, so what we need to do is figure out now, so I now know that the E of charge 2 is equal to 117 newtons per coulomb, which is K times the Q of that charge, divided by the distance, or squared. So to figure out what is the value of, well, let's rearrange for Q here. So Q is going to be equal to 107 newtons per coulomb times that R squared divided by K. What is the value of this R? So again, we just use the Pythagorean theorem to figure out what is the length of this hypotenuse. So just give me 1 second to do that. So I'm taking the square root of 0.5 squared plus 0.3 squared, which is 0.583. So about 0.58 meters, all to be squared, divided by K. Q is magnitude. Is then going to be the field, 117, times that distance, all to be squared, divided by K, Coulomb constant, 9 by 10 to 9, I end up with 4.4 by 10 to the minus 9 coulombs, and so that's the correct magnitude, and in order for the field at point P to point toward that charge, what we have up here is a negative 4.4 nanocoulomb charge. So Q2 is equal to negative 4.4 nanocoulombs. I think that should address all of the questions. Yeah, so this, in this context, the net field will point upward, and it will be equal to the magnitude of the y component of the charge 2. If you're curious what that is, it's, again, using the similar triangles. This is 60. This has to be 100. We go from 0.3 to 0.5 is the same ratio as going from 60 to 100. So the E net will be 100 newtons per coulomb in the positive y.